So last lecture we talked about the k nearest neighbors regression algorithm, and we talked a bit about least squares linear regression, just kind of typical regression. So we now have these two methods, and actually these two methods both have different parameters we can play with. So KNN has a number of neighbors we're calling capital K. That's the K in KNN. And regression, we can look at transformations and add covariates. So it has this parameter P, which is kind of the dimension of my design matrix, which increases with how many covariates I add. And so now that we kind of have some methods built up, we want to talk about evaluation. And we started last lecture by talking a little bit about evaluation, and we want to more deeply talk about it. And so we're going to talk about it but this lecture a bit next lecture. We're going to talk a little bit of theory and a little bit of practicality today. So let's talk about evaluation. So we had looked last time, for example, we had looked at RSS, which was the residual sum of squares. And RSS was, or maybe we should talk about RMSE. Doesn't really matter. Let's talk about RMSE. Nope, we didn't even talk about RMSE, did we? We talked about MSE. I think I can choose the right metric here. Okay, mean squared error. They're all one-to-one functions of each other. It doesn't really matter which one we talk about. But for example, MSE is a metric we can talk about, and we can use it to evaluate our algorithm. And in particular, last time we had talked about what we were calling the training MSE, so MSE train, and that was for my training data. So here I have my training data, and my training data is the collection of some points, yn, xn, okay, some capital N of these, and I use this training data to fit some f hat, some predictor function f hat, and one way I could evaluate how good this f hat does is I could calculate the training MSE. Well, MSE train, and MSE train, if I don't forget my square here, is basically the difference, the squared difference, or the mean squared difference of the true YNs minus the predicted YNs. So this YN hat is f hat of xn, and this yn is the true training y. So this makes sense. It's basically I'm going to look at the differences between my estimate and the truth. I'm going to square those to make it positive, and I'm going to take the average of it. And that's some metric that might tell me how good my approach is, my f hat is. But the question is basically, what do I care about when I'm evaluating a method? So let's write that down. When evaluating a method. And so let's make a list here. Things I don't care about, and maybe I'll say things I care about. Things I don't about, things I don't care about, and things I care about. So let's fill this out. Things I don't care about. What I really don't care that much about, generally, when evaluating performance of my predictor function f hat, is the performance of f hat on the training data. What I actually care about is the performance of f hat on new data I haven't seen before. Right? Basically, what I want to really do, the whole reason I'm training this F hat, is so that I can go out in the real world, collect more data, and accurately predict the response for that data. I don't actually care, in some grand sense, about how good my F hat is on the training data. Why? I already know the answer on my training data. What is the answer? The answer is the YNs, right? I have the YNs. The whole point of training data is I've not really collected the covariates, the XNs, but I have their responses, their YNs. So if I really just wanted to predict on the training data, I don't really actually care about trying to predict the YNs, because I could just go look it up in the table. I have them written down somewhere. And so I know what the answer is for those particular cases, right? What I actually care about is training it so that when I see a new instance of something that I haven't seen before, I can accurately predict it, right? If I'm training, we haven't quite gotten there, if I'm training machine learning algorithm to distinguish between kitty cats and puppy dogs, I'll give it a bunch of training data of kitty cats and puppy dogs, and I'll ask it, I'll train the algorithm to classify these things based on this collection, this corpus of pictures I have. But I don't really actually care for those pictures and sometimes getting it right, because I know, I've already labeled, I already looked at them, I know what the answer is, which is a cat, which is a dog. What's more interesting is now if I, put this in a robot with with a camera on it, and I want it to identify in the real world new instances that it hasn't seen before, and I want it to do automatically without my input, right? So that's the really interesting thing to do. And so for data I haven't seen before, I don't know the answer. And so that's what I'm really actually interested in predicting on. Okay, that seems all maybe a bit trivial. I just want to mention real quick, this is a very prediction-focused approach to machine learning, which is kind of separated from inferential statistics. So there are situations where I do care about my training data. So statisticians often care about inference on parameters, and they may actually care about relationships in a particular set of data. So it's not that that's never useful to talk about relationships for a particular set of data, but if I'm purely building typically just a prediction algorithm to predict things right, I'm not trying to infer some scientific relationship about the relation between my variables. All I want to do is build a black box prediction algorithm. I don't really care about how well it does on the training data, in some sense, because I know the answer. This is all a bit weird because in some sense, you're going to use the training data to learn it, right? So in some sense, you do care a little bit, in so much as you care that the algorithm should use that training data. But ultimately, my goal is to predict on new data. So this gives rise to a kind of dichotomy, and I'll maybe write this as some definition. We have already our training data, and in layman's term, our training data is the data fed to our approach to create F hat. So F hat here, and this is going to be kind of an important point here, F hat is a function of my training data. I feed it in my collection of XNs and YNs that I know. So that's training data. We also can define what we're going to call, instead of training data, test data. And test data is basically data from the same kind of data generating process, be that a natural phenomena, measurements of the same natural phenomena, pictures taken by similar cameras. So it's kind of this idea of this data generating process that generates the data. So it's data from the same kind of endpoint, but that wasn't used to, quote, train, that is to build f hat. So there's our dichotomy. Training data, which is basically the x's and y's you give it to the algorithm, and test data, which is going to be basically very similar to training data, but the algorithm hasn't seen it before. So it's this kind of untouched data that has not influenced the training of the algorithm. And we're going to have a scheme for evaluation of different f hats of our different machine learning models, algorithms, predictor functions. And our scheme is that obviously we're going to want to use the training data to, quote, train f hat, that is to build some f hat, be it linear regression, be it K&N regression, be it something, deep neural network machine learning AI. And we're going to train the f hat, and then we're going to evaluate f hat on the test data. So by training data, you can think of again as basically some pairs of xn's, yn's, n goes 1 to n. And my training data, my test data, so training data is these xn's, yn's. My test data is basically the same setup. I'm going to call them, say, xn star and yn star, where n goes from 1 to n star, which are just different. They're just a different set of data. So oftentimes what happens practically is you take the data, a whole data set that you could use to train the algorithm, you split it into two parts. One part you use to train the algorithm, the other part you use to evaluate it. So they're kind of part and parcel of the same data generating process in some ways. And there's this whole world of transfer learning and discussion about is the training and test data really from the same data generating process? And we might get to talk about that a little bit later in the course. But theoretically, they kind of need to match up. So oftentimes people just split their data off, do a training set and a test set. And what they do is they use the training data to train and they use test data to evaluate. And so what I mean by evaluate, right, you can basically partition, or maybe a better word is double up on metrics. So for any of the metrics we talked about last lecture, we had, say, RSS train, or we had MSE for the training data, or we had RMSE, which is the square root of the MSE for the training data. You could also calculate, once I get my f hat, you could calculate this for the test data. So you could do RSS for the test. You could have, MSE for the test, RMSE for the test. And so we talked about these last time. These are calculated on the training data. That is the data training data. That's data fed to the approach to create f hat. And then the metrics that one can calculate the test metrics are the exact same formulas, but just replace the training data with test data, with data that has not been seen before by the machine learning f hat. Why do we do this? I've kind of been hinting at it a little bit, but the main idea, and this is at this point not super mathy, but we're going to make this a bit more mathy. Don't worry. The main idea is that evaluating on the training data is potentially misleading. And I say potentially misleading, typically misleading. Doesn't have to be wrong, but typically not going to help you out when you're trying to compare different methods, right? So the intuition behind this statement about why it's misleading to evaluate your algorithm on the same data you use to train it, intuition. The intuition is that it's kind of like a circular argument. You're optimizing f hat to fit the training data, and so it's going to do well on the data you have optimized it to fit, right? The intuition is that it's kind of a circular argument, or say that, basically, right, so we said f hat is, what I do is I choose among all possible f's the f hat that minimizes the kind of the expected risk, right? Theoretically, that's what I do. We can actually calculate the expected risk, so you calculate the empirical risk, whatever. Basically, right, my f hat is chosen to minimize the expected, or in reality, the empirical risk. And so lo and behold, if I do this thing on, I minimize this loss, this expected loss, this risk on the data set, it is small for that data set. So let me just write that down so it's crystal clear. I train f hat, I choose my f hat by finding a f hat that predicts my training data well. That's the whole point, right? If for a regression, you're minimizing, you can think of it as minimizing a squared loss for k on n. You're kind of, you're again kind of minimizing some other kind of loss. You could write it down, but all of these can be written down in terms of, general idea is basically that you're choosing your f hat so that it predicts the training data well. So, not surprisingly, f hat predicts the training data well. You've chosen f hat so that it predicts the training data well. So it does predict the training data well. It's not an independent evaluation of how well the algorithm will do on new data, because you've basically chosen it so that it fits the existing data really well. And so how well does it fit the existing data? Pretty well. How well is it going to fit new data? I don't know. I haven't really evaluated it on data that it hasn't seen. And so it's kind of very fine, potentially, we're going to talk about in this course how to evaluate and try to avoid. It's potentially too fine-tuned to the particular training data set and not general enough to the actual data to figure out what's actually going on in the data generating process. So the result of this whole thing is that the training metrics are too optimistic, generally, on performance of f hat. That is how well it's actually going to do on new data. That is, i.e., basically what we're saying is that for example, the training RSS is typically going to be less than the test RSS. And so if we just were to evaluate on the training data, we'd be optimistic. We would say that the performance of our algorithm is better, the error is lower than it's going to actually probably be when we evaluate on an independent set of data. So the training metrics are too optimistic of performance of f hat on new or independent data. So let's look at a little bit more of a concrete example of some pitfalls, and this is going to make it hopefully crystal clear what's going on here, right? So let's again look at this K&N algorithm, okay? And here is going to be some example training data I might have. Maybe my training data looks something like this. So let's have a couple points here. And I have a lot of choices in how I'm going to build a K&N model, right? Which is one choice. But even within that K&N model, I can ask, for example, what value of K should I choose? Right, we have this tuning parameter K, and there's really not a lot of intuition about, there's some intuition, but the question is, where should it be for a particular data set? Here is a bad way to solve this problem. Bad way to decide. It doesn't seem like necessarily on its face it's a bad way to decide, but it is. The bad way to decide is I'm going to choose the value of K, number of neighbors I should choose, to minimize the training RSS. It doesn't seem totally insane, right? Because after all, we want it to do well on the training data set. The training data set is real data. We're trying to learn that relationship. And we have this value we have to choose. So why don't we just choose the one that's going to give us the best training RSS, right? Training RSS should give us some metric, kind of valuation metric, right? Question. What value of K minimizes the training RSS? Okay, so what is RSS train? Let's just write out the formula. Right, it's just yn hat minus y squared, right? It's just the sum of the squares of the predictions minus the truth. Oops, that should be a yn, right? Okay. How low can I make that training RSS? All right, and so here my YNs, these points here, right, are my training data. So the y coordinate is the yn, and the x coordinate is my xn. So we're imagining it's some kind of just one-dimensional x, okay? What about this? What if I fit this using k is equal to 1? If you remember last time, what k is equal to 1 does is it's going to just use the one nearest neighbor, and it's going to interpolate through my points. So it's basically going to say over here, the closest neighbor is this one here. And so I'm going to predict that value until I get to somewhere about here. And then the closest neighbor is going to be my second black point here. And so I'm just going to jump up and start predicting that level. And that happens until I get to be closer to this one here. So I'm going to probably jump down and predict that one. And then at some point I'm closer to this one, so I jump up, predict that level. And then until, theoretically, this is supposed to be flat, right? So it jumps down, goes like this, flat, until I get closest to my last point, and it's going to jump up and predict that, right? So it's going to do some kind of weird interpolation of my data. What's the training RSS, right? In this case, if I look at, so this is like my training data, x1, x2, x3, etc. This is y1, y2, y3, etc., right? Well, my predicted values, my red line here is basically my f hat, right? That I fit with my one nearest neighbor algorithm. What's my predicted value at x1? It's just y1. What's my predicted value at x2? It's y2, x3, y3. And so this whole thing is 0 because if for k is equal to 1, yn hat is just going to be yn, right? I'm interpolating my training data. So the RSS training is 0. Should I, right? So there's nothing particularly strange about this data. I generated some random points I drew here, and I said, let's minimize the training RSS. Turns out you can make it 0 if you choose k is equal to 1. Just interpolates my points. The training RSS is 0. So is it always best to choose k is equal to 1? So this is where being a statistician helps. I will say, as a statistician, what do we really want to do, right? Again, I don't actually care about predicting on this set of training data. I know what the y's are. What I actually care about is predicting on a new set of data. So the question that you should be asking yourself is, what is the true underlying model of my data? This is what I want to capture. I want to capture this, right? I want to capture what the true kind of non-random part of the model is, the true relationship. I don't want to just be interpolating a particular instance of it, because this particular instance contains noise. Maybe my true relationship is linear. Maybe this is the true relationship, right? That looks kind of right. Like, you could kind of draw a line through that. It looks pretty linear. And what I'm actually observing my training data is my data going to follow this line, but it's going to have some noise. So it's going to maybe do something. It's going to bounce around this line a bit, something like that. And so if I train my k and n with k is equal to 1, right, where I do this interpolation thing, right, where I go, I don't know, like this, right? What I really want to recover is that green line. And instead of getting this wonky red line, what I'm doing here is I'm not following the true underlying trend. I'm chasing the noise. And so what I really want to do is somehow capture this green line. I don't want to just chase the noise. Why is this bad? When I generate new data, if my true underlying model is this green line, the points fall on the green line, but then there's some random spread around the green line, what's the likelihood that the best thing to do is this kind of arbitrary red zigzag shape? My new data is in no particular reason going to follow this exact zigzag. Really, it's going to follow this green line, and maybe it will, the new data set will look like this if I generate new data, right? And so now, which one of these is closer to my new generated data? I would say the green line does a better job at capturing that trend than this arbitrary red thing that zigzags all over the place, which is not really capturing the true fundamental data generating process. It's just capturing the noise of the particular data set, which I don't really want to capture. I don't care about the peculiarities of this particular data set. I care about the general trend so that I can do well, right? If we go back to what I actually want to do, this is what I actually want to do. I want to find f hat so that it minimizes minimizes my expected loss. That is, if I pick new data, I want to pick the F that will minimize the loss or minimize the error that I expect to get on new data. I don't want to pick the loss that just particularly minimizes the error for this one data set, because the new data sets aren't going to follow that particular trend, and I'm going to do a better job by capturing the true underlying trend rather than following some noise in the data. And so just to write that in words, when I generate the new data, when I generate my new data, it won't follow noise, but the underlying trend. That's basically what I'm saying. So, so as I wrote above here, what's going to happen is that my training RSS is going to be lower than my test. In this case, my training RSS is 0 for this example. But if I generate new data or have another data set, that if I look at the difference between the red line and the blue points, that's not 0. I'm definitely not going to be 0. And actually, I'll probably have a better generalization error or a better training error if I use the green line, because it's going to really, in this case, assuming the true trend is linear, and so in this case, it's going to capture it better. I generally don't actually know what the true trend is, but these principles still apply. What we call this overfitting, which is basically optimizing too much to a particular training data set and not capturing the general underlying trend, which is really what you want to capture. Okay. So let's draw a famous picture here. Here's going to be the famous picture. I'm going to talk about my x-axis here is going to be my flexibility axis, where on the right here, I'm going to have a more flexible method. And on the left here, I'm going to have a less flexible method. And so, for example, more flexible is KNN with a low value of K, or linear regression with lots of added covariates. That is a high value of P. Those are two examples. Now, on the less flexible end, I would have something like KNN with a, it should be KNN with a high, nope, I'm right, low value, right? Like K is equal to 1. On the left here, I have KNN with a low value of K, like K is equal to, my writing's wrong. KNN with a high value of K, right? So if KNN is the number of set of training points, we saw it makes a flat line last time. Or I could have, say, for example, linear regression with a low value of P that is not many covariates. Okay. And let's plot some error metric, or some, maybe we call it evaluation. So, for example, e.g. RSS, mean squared error, whatever you want, pick your favorite. And I'm going to plot two curves. The first curve I'm going to plot in blue is going to be the training metric. And that is, I'm going to fit. So what I'm going to imagine I'm doing is I can move back and forth on this axis with whatever methods I want. I can try high values K, low values K, more covariates, less covariates, move back and forth here. I'm going to do that with my training data. Then I'm going to fit. I'm going to fit the method and evaluate it. And I'm going to evaluate it both on training data set, and I'm going to evaluate it on a test data set. So I'll have another line. Let's make it green, which is going to be my test metric. Okay. And for my training metric, basically the error or the evaluation, inverse of the accuracy is going to go like this. So this is my training metric, where lower is better, generally speaking. And so that's basically the curve I'm going to get, okay? And why that's going to happen is that I'm basically going to really start overfitting my data. So like, for example, I'm going to have like k is equal to 1 here and k is equal to n on the left, right? So if I have, eventually that will hit, for k and n, that will hit 0, right? So as I increase the flexibility, I'm going to be able to, as we did in this example above here, I'm going to be able to fit this training data better and better and better and better. Eventually, for some models, you can interpolate it. You can't always do that for linear. Well, I guess you could for linear regression. If you add enough covariates, you'll interpolate your data also. We didn't really talk about that, but you could. If p starts to go to n, you'll start to interpolate your data for linear regression. Right? So as I add more and more covariates, or I increase or I decrease the number of neighbors I'm looking at, I'm going to fit my data better and better and better, right? I have a more flexible method. So here, what I mean is that, like, let me just draw a picture here, right? So here is maybe my training data, and here is a inflexible method, or a simple inflexible method, which is it's just a line, and then I could have something more flexible, more wavy, something like that. This is more flexible. Okay? And so you can see as I increase the flexibility, or I increase the complexity, flexibility, complexity are kind of the same thing, I can follow the individual kind of these training data points better and better and better. I can fit them better and better and better as far as the training metric goes. So if a really simple model, I'm going to have relatively high training error. And because something simple like just a line, inflexible model without a lot of covariates, for example, some simple linear regression doesn't do as well a job. And if I so this is my training regime. If I do the same thing with the test data, test metrics almost always are going to lie above the training metrics, right? But it's probably going to end up looking something like that. It'll look like some parabolic or some quadratic curve, generally speaking. I mean, it's a quadratic or whatever. It's going to start off decreasing, and eventually it's going to hit some low point, and then it'll start increasing again. This is what we call the sweet spot. I want to be here. All right. We want f hat to be there. All right, so for the test metric, where we evaluate an independent test set, event first is going to start decreasing as I fit my as I have a more complex model, more flexible model, which is going to be better able to capture the true underlying data generating process, the true f. But if I start having a too flexible of a model, I might start getting into this kind of regime where I start what we're calling overfitting, where I'm chasing, instead of the underlying true model, I'm just going to start chasing the noise. And for the training metric, it's just still going to keep decreasing. So the training error is still going to keep decreasing because it's kind of a circular argument. But for test data, our performance will actually start to degrade. We will have a worse evaluated metric there, and so we'll actually start to increase again. Right. So this is to the right here of kind of my sweet spot. This is what we call overfitting, and to the left here, you could call this underfitting. And really, we want to do neither. We want to hit that sweet spot. We're minimizing. So you notice this is the minimum. This test metric is basically the expected, the curve of expected risk, or the curve of empirical risk. We basically want to hit the minimum of that, right? We want f hat here. We want f hat is the minimizing f for our risk, right? I mean, so that can be difficult always to hit exactly, but that's ideally where we want to be. Typically, overfitting is the sin that people do because they get confused and they start looking at the training metric. Don't really need to look at the training metric that much, not particularly useful in general. What you really want to do is look at the test metric, and you want to use that as your guide about how well your model's doing. So if I go back to my problem where I said, how do I choose what value of k I should have for k and n? Minimizing the training RSS is a bad idea. Minimizing a test RSS, not as bad of an idea. We can talk about that. Maybe we'll have a little bit on that next lecture. There's a little bit to be careful there, but it's a much better idea, let's say. It will lead to a better performing generalizable model. There's a caveat there. Let's come back to it, but much better idea. And so typically people overfit because they want, we want a really complicated model. We want some, neural network with 5 million parameters that, is way overfit for our training data. People really don't understand. This happens in real life. People don't understand that they're paying attention to the wrong thing and they're overfitting their method. Less often, people underfit things, though it's a real thing to pay attention to. But typically, the sin is overfitting. Okay. So let's talk about, in the last couple, say 10 or so minutes here, let's talk about how we can avoid this and in real life. And next lecture we'll talk about the theory. We'll make this probabilistic. We'll put this all in a probabilistic framework. Because I'm a statistician and this is I'm calling it a statistical learning kind of data mining course. So how do we solve this? This IRL in real lives. Okay, so typically in real life, what you get is I get some data set, right? And the data set is just a bunch of data. And what you want to do is use this data set, want to use to make f hat to predict well. All right, I want to predict things well, and so I want to use this thing to predict things well, and I want to use it to predict things I haven't seen before. I really care about the performance on my training data. I want to use it to predict data I haven't seen before. But I don't get given from on high a test data set. In reality, I get an access password to a SQL server, and I have to download the data from there, and I have to deal with everything myself. So what people often do when they're building these things is I will take, so we can call this approach 1, which is maybe called a validation set. We're going to spin off what's called like a some people call validation set. We're going to call a test data set. So here's the diagram. I have my data, and I'm going to split it into 2 chunks. Chunk number 1, I'll call my training data. And chunk number 2, I'll call my test data. And I'll typically split off some percentage, some p% as my training data, and I'll use the 1 minus p% as my data to evaluate. Typically, maybe, p is maybe like, sometimes you use p as 50%, sometimes people use, say 90% test training, 10% testing. Those are kind of common ways to do it. And on my training data, I fit the model, and on the test data, I evaluate. And so basically, you do this split shall I say, randomly, just to ensure that we're not, like, the data is ordered in a certain way, like by date, and you just say, I'll pick the first half of the data set, and that will be, the first half of the rows, and that will be my, my first data set, and the second half will be my test data or whatever, right? That's bad, right? You really want to kind of randomize the data set first, so you're not including any biases in there. So this is a great idea, right? So you test, train, split is a phrase you'll hear. Test / train, split. Split the testing data, training data. Some percent train, the other percent you use to test. Typically, the testing data is a smaller percentage. Doesn't really matter though. And this doesn't run into your problem because you're evaluating on the test data. And so then if I want to like play around with the parameter and say, oh, okay, what are the different values of k to use? I can try a bunch of different values of k, train it for all those different values of k for my k and n model, test it, and there is no bias in there. Or we can use that. Well, let's talk next time a little bit, but we can use that that will better choose a more general model because I'm not using my training, say RSS, which is, which would be the circular argument to evaluate it there. I'm using an independent data set where I have not overfit to that. There's not a risk of overfitting to it. Okay. So that's the simple way. The more complicated way is called cross-validation. And this is just basically a variation on this idea. And cross-validation, what we're going to do instead is we're going to take our data and we're going to split it into some number of sub-data sets. And let's say randomly split into, quote, folds. What do we want to call it? Data 1, data 2, etc. Right? And so typically, although this is confusing with k and n, people like k as an integer. We could call this k fold. Nothing to do with k and nk, but just some integer. K fold cross validation. And I'm going to split my data set into k different folds. I'm randomly going to split it into k different folds. And what I'm going to do with these folds is cycle. I'm going to cycle through all my folds, and I'm going to do the following for each of them. So this is like a for loop. Like for folds, what I'm going to do is 1, train on, I don't want to say this, I'm going to train on all folds but maybe the kth. So maybe I should say for k goes 1 to capital K, which is how many folds I have. I'm going to train on all folds but the kth. So for example, in the first iteration, I'm going to say little k is 1. I'm going to hold off that data 1, that first fold. I'm going to train on the other folds 2 through k, and then I'm going to evaluate on the kth fold. So then I'll evaluate on data 1. In step 2, I'll get some metric, right? In step 2 of my loop, I will hold out the second data set, train on the other ones, and evaluate on data 2. So this is iteratively basically doing this previous validation set thing, where I'm going to iteratively do it. So at some point, every piece of data is used to train it, and every piece of data is used in the evaluation of it, right? And I'm kind of cycling through and switching out which pieces are in the validation set, and which are in which are in the training set, and which are in the test set. So at the end of the day, I'll get a metric at each point in my loop. The metric when evaluating data 1, data 2, data 3, all the way up to fold k. So I'll get some k metrics. Let's say M1, M2, corresponding to each iteration of my loop, which is, a train on everything but the M1 be train on everything but 1, evaluate M1, M2 is train on everything but 2, evaluate and 2, etc., etc. And then I can summarize into a final metric. And my final metric may be, so for example, M is maybe my metric, is maybe the median of all of my kind of sub-metrics from each of these folds. So I just basically say you can take the mean, the median, whatever. Pick your favorite way to summarize some numbers and do that. And so this is kind of a more fancy version of it, but it ensures that at some point every piece of data makes it into both the training and test data set, and then it kind of summarizes everything together. And so this is called cross-validation. So I think this is a good point to stop here. Next lecture, we're going to talk about one more variation on cross-validation, which is called nested cross-validation. And we're going to have a little discussion about nested cross-validation. It's a little bit more advanced. And then we're going to put some theory to all of this. We're going to, not too bad, just some expectations, some simple probability. It gets us a lot, though. And we're going to talk about this whole in particular, this figure here. We're going to talk about this in the probabilistic context. Can we actually talk about this in terms of a probabilistic model? So this is kind of a statistical data mining, statistical machine learning course, and so we'll put some math behind it. But we'll stop there for now.